is yours.
Uh, Thanks, Luca. This is going to be an even shorter and therefore faster spoken talk than my previous one. And yeah, I'll be talking about using formal methods to discover a bug in the Chapel compiler, and I hope you can hear me. Uh, all right, so basically I have a story in three parts. The first is that I found a piece of compiler code that I was having a lot of trouble thinking through. And in particular, this was a piece of code that handled scope lookups of variables and functions. So what I did is use the alloy analyzer to model my assumptions about the code and the code's behavior. I had a little bit of background, or I had no background in alloy, but I had a little bit of background in formal and temporal logic, which definitely helped. Um, this modeling led me to discover a bug in the compiler that we hadn't caught before. I then fixed it. So recreating the bug required quite a bit of gymnastics, so it probably wouldn't have occurred in practice, but I sleep happier knowing that the Chapel compiler is more robust. All right, so let's talk about Chapel scope lookups to motivate the bug. So suppose you're looking at a call to foo somewhere within a bigger Chapel program. Where do you look for foo? It turns out the answer is quite complicated and depends strongly on the context that surrounds foo. Also, the order of where you look actually matters because Chapel prefers method calls to global non-method functions where possible. And furthermore, it prefers near functions lexically to functions that are further away. So consider this little example where I have a single module, and within this module, I have a record. Also within the module, I have two procedures called foo. One of them is a method on R, and the other one is a non-method and has very little to do with R. And finally, I have a third procedure, which is also a method on R that calls foo. Now, which foo do we refer to here? So in fact, if they only existed by themselves and weren't both listed, both r.foo and the module level foo would be valid candidates. However, we give priority to methods over global functions. And so to handle this kind of case, the compiler would would perform two searches. First, it would search the record R and the scope in which it's defined, which is M1, only for methods named foo. And then if that were to fail, even though it won't in this case, it will search the scope in which the call occurs, which is also the scope M1, for anything, including non-methods. So in this case, it would find foo if it had failed to find r.foo prior. So you might notice from this that we looked within M1 twice. We looked once for methods and once for non-methods. And then also, to complicate things, sometimes we look only for public symbols because, for instance, if you have two modules, M1 and M2, and you use one module from the other, we don't want to bring in private variables from M1. And so we search the scope of M1 only for public symbols. So basically, the constraints on the Chapel compiler are as follows. The first is that we want to restrict the priority or respect the priority order. So this means listing methods over non-methods, and as a result, we ended up searching scopes multiple times. Furthermore, we want to avoid any extra work, including redundant researches. So if for some reason we've already searched a scope for all symbols, we don't need to later search it for all public symbols because all public symbols are a subset of all symbols. And that motivates the design of Chapel scope resolution features. And so this is encoded in the compiler by a bit field, which basically stores properties of things that we currently care about. So you have a bit flag for public things, a bit flag for non-public things, so private things, a bit flags for methods, and a bit flag for non-methods. And to avoid redundant searches, for each scope that we've searched, we save the flags we've already searched with. And when searching it again, we don't include these flags a second time, and that saves us some work. So in practice, this used to be handled by only two bit fields: filter, which specifies which of these properties we're currently looking for, and exclude filter, which specifies which things we've already looked for and no longer want to see. So then, this is a grossly simplified segment of compiler code. We basically configured the filter with these various flags depending on the context of the call. So if we're looking only for public things, we'll add the public flag. And if our context is not a method call, we can include not method to save us some work. And then the exclude filter, which rules things out when we're searching, is populated from our previous searches, which I stored in the variable previous filter. But once you perform multiple searches, you actually have to combine the current previous filter with the new previous filter because we've made two searches. And this was done using a single bitwise AND. And if you think about it, this is a fairly reasonable approach. However, it is an approximation, and the code notes it as such. So I don't like approximations. Given the code noted an approximation, I went looking for problems. But none of our test suite failed. So all the language tests that we had written for scope resolution passed, and all the programs we tried seemed to work. So I thought, well, if only there was a way I could automatically check all these possible cases and see if it's possible for the compiler to run into a case where there'll be problems. And that's where I used formal methods. So the method I used in particular was called model checking, which basically entails formally describing the behavior of a system using mathematics, and then having a solver check whether the properties you've described hold. Alloy, which is what I used, is an example of a model checker, and TLA, which I won't talk about, is another famous example. So these model checkers use logic, in particular temporal logic, but that builds on regular old first-order logic, which roughly looks like this. So encoding this statement in first-order logic, Bob has a son who likes all compilers. It is translated into there exists some entity that is Bob's son, and for any other entity that's a compiler, Bob's son likes that compiler. And in Alloy, we use the word sum and all instead of these fancy math symbols, which probably appeals to us programmers. Temporal logic extends first-order logic with additional operations that describe how things change over time. So you can say, for instance, that a statement always holds true. One example of this is physics doesn't change, so like charges will always repel, and they have always repelled. And another statement is think that something will eventually become true, even though it might not be true right now. For instance, even if it's nighttime, the sun eventually will rise again. And finally, Alloy lets you relate previous and current variables by saying that in the next temporal state, the previous filter might look like the and of the current filter and the previous filter. This is pseudocode, however. So basically what I ended up doing was modeling my C++ code as a sequence of state transitions, where the state is basically the variables that I have. So for instance, I have a filter variable that gets ORed with public. And basically what I do is relate the current state of the filter with its next state by saying they're the same, except now the public flag is set. This might remind you of for logic, which describes programs' behaviors by saying if some precondition holds before a program is executed, then after the program is executed, this postcondition Q holds. And if you have multiple statements, which of course the compiler does, you basically have to introduce intermediate states. So if you first add a public flag and then a non-method flag or a method field flag, you take the current state and say that one intermediate state will have just the public flag added to it. And then that intermediate state and the final state are connected because the final state also has the method flag. And this looks very much like sequencing Hoare triples in which there's some intermediate description of the state. So you start in a state described by P, the first statement runs, the state is described by Q, the second statement runs, and the final postcondition R is the case. And if you have conditionals like these, and you don't want to go much deeper, you can basically model them as running or not running, which I model in Alloy using ORs. So either the next state has a public flag or the next state is exactly the same as it was because the condition didn't run. And I have that for both statements. And finally, what I did was say, so to find bugs using Alloy, what you have to do is ask, and I understand that I'm running out of time here, is ask, are there any bugs? And basically what you do is you make a claim in logic that says, hey, I assert that there is a claim, prove me wrong. And if it can't prove you wrong and it finds a counterexample, then there's a bug. So basically this really long logical formula says, if you make several searches using this stateful mechanism, then after a few searches, you will have another search that will occur and come up empty, even though it shouldn't have come up empty because you broke it. And unfortunately, Alloy found an instance of this. It took some magic to interpret the results of Alloy. They look pretty much like this, lots of shapes and arrows and long variable names. And there's a certain sequence of steps that takes to create this bug. And in fact, the program that is reproduced is this, which would really never occur in practice. It requires 3 nested modules. So a top-level module within which there's a container module within which there's another module, and lots of weird public uses and other statements. However, in the compiler model that I was creating and in the real compiler back at the time, you would look up X and come up blank, even though you shouldn't. And this bug is now fixed on main. And since Dyno's scope resolution is used by the Chapel compiler, you are living in a world where this bug used to affect you, but no longer does. And that's my talk. I have extra slides, obviously, that, oh, you can also read more about this by scanning this QR code. This is an article on my blog that covers it in much more depth than I could give in 10 minutes. Actually, a little more than 10 minutes, thanks to the early start.
Cool. Let's thank the speaker with a warm round of applause. Are there any questions from the audience? Jade?
Hi, Daniel. Do you think there's other cases in the compiler that would benefit from seeing techniques like this to kind of make the compiler more bulletproof?
I haven't run into anything that is manageable. So one problem with formal methods is they're typically relatively heavyweight. So you need to do kind of a lot of work to model the full behavior of a system. I haven't found anything right now that could easily be modeled in such a way in a reasonable amount of engineering time, but I'm always on the lookout.
Thanks.
Alrighty, thanks. I yield the floor.
Actually, I have a question. How much effort do you think, like in terms of like human effort, human hours work to like verify the whole Chapel compiler?
The whole Chapel compiler, years, probably years, of multiple engineers, I think. It's just not viable. I mean,
Yeah.
there's only a few formally verified compilers out there. I think CompCert is the famous one. And that one isn't even modeled using model checkers. It's actually modeled using a different approach called proof assistance. Well, it's not called that. It's modeled using proof assistance and dependent types and stuff. And even that, isn't even a fully fledged, particularly powerful compiler. So I think these approaches are best restricted to either smaller subsets of the systems, like the scope resolution pass, or high-level modeling that doesn't involve kind of modeling the entire machinery of the compiler.